Okay, this is the Chapter 2 review. Number 1, we're looking at 4th, 5th, and 6th graders and asking them if good grades, athletic ability, or being popular was most important to them. Okay, so our explanatory is kind of what happens first. Okay, the first thing we know is what grade they're in. Okay, so that would be their explanatory variable. The response variable would be what are we asking them about, which is what is most important. Okay, so whatever their grades or athletic ability or being popular, that would be what's most important to them. Okay, so we have our explanatory and response variable here. Okay, making a bar graph here. So across the bottom is our explanatory. So they're either in 4th grade or 5th grade or 6th grade. And then we got to go percentages here, 20%, 40, 60, 80, 100%. Okay, you can go by tens or whatever you went by. And then we have to find the percentages for each one. So if we look at, let's go with good grades first for all of them. Okay, so this one we have 49 out of the 92 total 4th graders, and it was like 53%. So 4th graders was at 53% for good grades. For 5th graders, it was 50 kids out of the 108 kids. So that gives you about 46%. So 5th grade is less. And 6th graders, we had 69 out of the 135, which is like 51%. So right in the middle. Okay, so the first ones here, I'll label these as good grades. Now, we can already see that there's not an association. There is an association between grade and what is popular, right? So since these are all not the same, we know that there is an association. Depending on what grade they are, it does change the outcome of what they're going to say. Okay, but we can finish up. This would be 24 out of the 92 people, which would be about 26%. So 26 in addition to that would be 79, so almost 80 here. And then I know the rest of it, out to 100%, would be the being popular. So I'll say this one going across here is the athletic. And we'll say the one that's left open is the being popular. Okay, for 5th grade, we had 36 out of the 108 total 5th graders was 33. So 33 plus the 46 that's already there, we came out to be about 79. So right about there. Okay, and then 6th graders, we had 38 out of the 135 for athletic, which is about 28. So 28 plus the 51% that's already there took you up to 79 as well. Isn't that interesting? All three of those came up to be 79% there. Okay, so almost not an association, but these are all different, so there is an association. Okay, so yeah, there's our bar graph. Okay, our segmented bar graph. So letter C, based on that, is there an association? Yes, there is an association. You can't see. I need to move this up for you guys. Yes, there is an association. What's most important changes from one grade to the next. Okay, and it doesn't change much, but it does change just a tad little bit there, especially for the good grades part. Okay, so that's number 1. Number 2.
You can see I typed in the data already. Part A asks us for the explanatory and response. The explanatory is our x variable here, which was our average temperature. And a response was, after we had the average temperature, in that month, how long did it take for them to crawl, the average age? So you can see that right here. So that's part A. Part B, make a scatter plot to display the relationship. So you type it in here, and if you hit this little thing there, zoom fit, we get a good scatter plot there. So you can just kind of sketch that. It doesn't have to be real accurate. Part C, describe that relationship. Okay, so we want to think SOX. So in SOX, I'm sorry, not SOX, SOFA. SOX was last chapter, right? With just linear. Okay, SOFA, I would say, and you can, if you wanted to get the equation here, you could get the equation. Let's just do that real quick. Y1 tilde m x1 plus b. Okay, so tilde here. Okay, so you can see our R value comes up to be negative 0.69. So right around 0.7. So that gives me, it kind of says it's a moderate, okay? Moderate strength. Outliers, maybe this one down here, okay? Down here at this point here at 52 weeks. Possibly at a temperature of 52 degrees. Form, it looks pretty linear. Okay, linear is a good idea for it. And the association is it is a negative, which is saying as the temperature increases, the age at which they crawl decreases. So that's kind of interesting, isn't it? Okay. And then part D, give an estimate of the correlation. Well, we actually did find the correlation here, right? We'll say our estimate is negative 0.7. Okay. Hopefully it's somewhere around there for your estimate. Okay. So that is number 2. Okay, so for number 6, okay, 2 and 6 kind of go together. We use technology to calculate the equation of the least squares regression line. And we type that in here, y1 tilde m x1 plus b. And we get an equation roughly about y hat equals a negative 0.08 x plus 35.6768 if we round it. Okay, so roughly that's our line of best fit. Part B, use a scatter plot and describe what is unusual about the point representing May. So May was the one with x equals 42, this point right here. So this point here is May. What is unusual about that? The temperature isn't that unusual, right? The temperature is kind of right in the middle of all the other temperatures, but the crawling, the amount of time it took to crawl was low, okay? So the time to crawl was low, a lot lower than expected. Okay. Part C, how does the point affect the least squares regression line? Okay. So look at this line here. We have our slope and we have our y-intercept. Now, let's say I take this point out of there. Okay. So this is the one with 52. I'm going to go up here, get rid of this 52, and this one. Okay. So if we look now at our line. Okay. So our slope didn't change a whole lot, but our y-intercept went from 35.6 to 38. So you can see the slope. So remember, if a point is kind of in the middle of the x's, it doesn't do much to the slope, but it'll bring the y-intercept down. So in this case, if I get rid of it, it takes the y-intercept up. Okay. So part C, how did it change? The slope did not change much. The y-intercept increased without it. Okay, so that is number 6. Now, just a little review. If I put a point way out here, okay, so if I put a point right here, like at 132, okay, let's see what that does to it. So my x is 132. Notice that really changes the slope and the y-intercept. So the slope came up and the y-intercept came down. Okay, so you can think about what kind of outlier it is and what kind of impact that has. So if I get rid of that 132 there, okay, you can see how its slope went down again. Okay, so that's number 6.
Okay, question number 3 says that they noticed that a positive correlation between the number of calculators owned by high school students and their math achievement. So, just because we have, if somebody owns more calculators, their math achievement has been higher, is what he's noticing, okay? So he says, oh, I'm going to go back out and I'm going to buy people more calculators. Is that going to improve the achievement? No, not necessarily. The flaw is that correlation does not equal causation. Just because I see a correlation that one affects the other in a positive way doesn't mean that one thing is going to affect the other and cause the other thing to happen. Okay, so that's the idea of number 3.
Okay, so this is question number 4. Here is the scatter plot. Okay, so number 4, you can sketch the scatter plot for part A. Okay, for part B, calculate and interpret the correlation for this data. So you don't have to go through and do it by hand. We're just using the calculator here. So y1 tilde m x1 plus b. And our correlation is 0.5653. Okay, it says and interpret. Okay, so it is a positive, moderate, or weak correlation. Okay, so positive and 0.56 is kind of moderate to weak. So that's our interpretation. Part C, what effect does the pair 70-71 have on the correlation? So 70-71 is the one point right here. Okay, if that point was not here, what would happen to that line? Okay, so let's actually take it out. If I take 70-71 out of there, what happens to that line? It changed quite a bit, didn't it? And our correlation became stronger. So that point that weakens the correlation. So it was 0.5, right? So without it, it's 0.6. So 0.5 is weaker. So it weakens the correlation because it's not close to the line of least squared regression line. Okay, part D. Okay, so explain how the correlation would change if the heights of the women were now measured in centimeters instead of inches. So if I change the centimeters instead of inches, R stays the same. So there's no change with that.
Okay, number 5, we have latitude and the mean temperature in July of 12 U.S. cities here. We want to predict the mean July temperature in Fairbanks, Alaska, which has this latitude. Latitude is my x variable here. So for part A, I want to plug that latitude, that in here for the x. My prediction for the y would be 106.5 minus 0.782 times that 65 degrees. And let me get my calculator and find it. And that comes up to be a prediction of 55.67 degrees. Okay, part B. Los Angeles, California has a latitude of this, and so we have the latitude of 34 and an actual temperature of 74. So let's find the residual. Okay. Residual is equal to our actual minus the predicted. Okay, the actual here is 74 degrees. To find the predicted, I have to plug that 74 in there. So I plug in 74 right there. I get 48.632. So 74 minus 48.632 gives me 25.368. Okay. There's the residual, and doesn't tell us to interpret it, but it would be our actual. Okay, it's this point right here. This is kind of weird because No. Okay, yeah. Anyway, part C. Part C, interpret the slope. So the slope of our line is this number right here, negative 0.782 over 1. And remember, slope is the change in y, so the y is the temperature, over the change in x, which is our latitude. Okay? So for every increase of 1 degree latitude, we predict the temperature to negative, so decrease 0.782 degrees. Okay, so that's our going down for that much temperature for every 1 latitude increase. Okay, D, the y-intercept. Okay, the y-intercept here, we look at our equation. Our y-intercept is 106.5. Okay, and that would be, that is when our x is a 0. So that would say at latitude 0, we predict temp to equal 106.5 degrees. So that does have an application here. Okay, so that's number 5. Okay, number 6 I did right after number 2. So if you're looking for that, go back to note that one. Okay, number 8 talks about the problem we just did here, the latitude and this, and it creates the residual plot. Remember, residual plot is the residuals here, right, are all plotted here. So these have 2 positive residuals, very small, a residual there, a larger residual there, okay? The residuals there, okay? So is it appropriate that it is a linear model? Yes. And it is appropriate because it's a good scattering above and below. Zero. Okay, so we have a good, kind of good scattering there. You could maybe say it's not great if you kind of look at that pattern there, but I think for the most part it's okay. Okay, part B, the standard deviation of residuals gives us an S is equal to 6.4. Okay, interpret this value. So remember, standard deviation is how much it varies, and of a residual is our error. So this is how much error there is. So when we're predicting the July temperature from latitude, we are off or make an error by 6.4 degrees on average. Okay, so when I make a prediction, I'm off by maybe 6.4 degrees above or below that, whatever that prediction is on average. Okay, part C, we have an R squared value is 0.277. Interpret this. Okay, we can say that 27.7% of the variation in our Y, which is the temperature, can be accounted for by the latitude. Okay, so is latitude a very good predictor of the July temperature? Only 27% of the temperature can be predicted by the latitude, so not a great predictor. Okay, so that is number 8.
Hey, here's number 9. You can see has the years since 76, year I was born, by the way, 1976, great year. Anyway, 76, the number of employees, there were 7 employees. 1 year later, there were 9 employees. 2 years later, 13 employees, etc. Okay, and this is of Microsoft. See how many employees are. So 10 years later, in 86, there were 1,442 employees. I'm not sure how many there would be now, but quite a few. Okay, so you can see this graph here, and you can definitely tell linear is not the best thing here. Okay, so part B asks us to find the quadratic model. So the quadratic model, we would type y1 tilde ax1 squared plus bx1 plus c. And we can see our quadratic model has the a, b, and c right there. So it'd be y equals 23.29x squared minus 108.91x, I just go to 2 decimals, plus 82.19. Okay, so that's our quadratic model. Part C, the exponential model. So part C, the exponential model, we would use y1. Okay, so a times b raised to the x1. Okay, so our exponential model is y. All these should be y hat, by the way, because we're predicting. Anyway, a is 16.74 times b, which is 1.56 raised to the x. Okay, just a little side note, that means that there's been 56% increase every year, on average, 56% increase. Okay, anyway, part D. Okay, we want to do some residuals here, okay. Also, let's just look at this real quick. Which do you think would be a better representation? Would the quadratic model be a better graph or the exponential? Okay, the exponential has an r squared of 0.99. The quadratic has 0.98. Okay, so both are okay. Both are good representations of the data. I would say that the exponential is probably a little bit better though. Okay, there's just one point here that kind of sticks out there a little bit, but for the most part, exponential looks pretty good. Okay, for part D is looking for if we have the year 1981 and 5. Okay, 1981, how many years after the 76 is it? It is 5 years later, so we're looking at the 0.55. So this point right here, okay, is the point that we're looking at. So what's the residual of this point? Well, we know it's below the line, so it's negative. Okay, so it says using each model. So let's do the exponential here first, since we have the graph up here. So using the exponential model, it's below, so it's going to be negative. Our actual is 5. Predicted, you can find it 2 different ways. Okay, if I go here on this line of best fit, looks like it's a little bit more, a little less. There, 155.7. You can also take that 5 and plug it into this equation with the a and the b, and you get that same value there. Okay, so you subtract. I'm sorry, our actual was 128. Okay, so 128 minus 155.7. So 128 minus 155.7 gives a residual of negative 27.7, which means, you know, we said it was negative, right? It's below. So our actual was 27.5 employees less than what we were predicting. Okay. Now, using the quadratic model, okay, we're still looking at the same point. Very close, isn't it? So the quadratic model, our actual was 128 from the point on our table. Okay, so just real quick here, the point right here, actual is 128, and what we're predicting, if I bring this down here to 5, is 119.9. Okay, so 128 minus 119.9 gives us a residual of 8.1. Okay, so this one was just a tad bit, 8 employees more than what we were predicting. Okay, so that's part D. And then part E, explain how you could use the residual plot for determining which one's better. Okay, so if we look at this plot right here, the residual plot, we'd have 1 below, kind of equal, 2 above, above, below, 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 above, below. Okay, so we look for a good scattering. That looks like it would have a decent scattering. Okay, and then this one, notice here, the points are a little bit farther away from the line, but with also a very good scattering as well. Most of them are below here, whereas these are above, right, a little bit. So look at a residual plot and look for that good scattering if they give you one. Okay, so that's number 9.